Okay, so this is for chapter 19. Okay, so we'll start on the first question. The first question is predicting whether each process is spontaneous as described. The first is water at 80 degrees Celsius gets hotter when a piece of metal heated to 170 degrees Celsius is added. Second question is at room temperature, CO2 gas and H2O gas combine to form table sugar. Three is rubbing alcohol vapor C3H5OH gas at a pressure of 1 atm condenses to liquid rubbing alcohol at a normal boiling point of rubbing alcohol 97.2 degrees Celsius. So because we are going to use some of those scientific law and some of those common sense to decide those process spontaneous or not. So for the first situation, based on what we learned in Chem 113 about the heat, we know heat flow from hot object to cold object. So when we have water at 80 degrees Celsius and we have a metal at 170 degrees Celsius added to it, and we expect the water were getting hotter, the metal were getting cool. So therefore, that first situation is spontaneous, or the first process is spontaneous. And for the second process, at room temperature, we know that there are CO2 gas and H2 gas in the air. In the air, we breathe in, breathe out. And we never see them combine to form sugar. So therefore, from our experience, we can see the second process is non-spontaneous. The last process is about condensation and vaporization equilibrium. So when we see this process as described in this paragraph, so we know that the alcohol vapor is at equilibrium with the liquid alcohol. So that means we cannot assuming all the vapor will condense into liquid. Oppositely, we cannot assuming all the liquid will vaporize become the vapor. So they are at equilibrium. So therefore, both liquid phase and gaseous phase of the substance coexist. So therefore, we see the vapor will not condense spontaneously to the liquid. So therefore, the process 3 is non-spontaneous. So we have a spontaneous and non-spontaneous, non-spontaneous. So therefore, the answer is B. Okay, so the second question is predict whether delta S is positive or negative for each process, assuming each occurs at a constant temperature. So we know delta means change, S means entropy. So therefore, delta S is the change of entropy. So we know some of those qualitatively, we can compare the entropy S for different situations. So for example, for the same amount of example, entropy S has the following trend, which means the entropy in the gas phase or gas state is larger than the entropy in the liquid state, which is larger than the entropy in the solid state. So therefore, for the first process, we can say H2O liquid become H2O solid. So if we have the same amount of H2O, so going from liquid to solid, the entropy decreases. So if entropy decreases, which means delta S is negative. For the second process, we can see we have PB2 plus ion in aqueous, which means in liquid, and then 2Br negative 1 ion in aqueous, so that's also in liquid. So they combine together to produce the precipitate, which is solid. So this process is kind of we going from liquid, also going from liquid to solid. So therefore, when ions in liquid combine into solid, we expect that entropy S also decreases. Therefore, for the second process, delta S is also negative. So therefore, we have negative and negative, which match in the answer A. Problem number 3 is in each pair, so we have 2 pairs of substance, and choose the system that has greater entropy. So the first pair is we have 2 something. One is 1 mole of H2O solid at negative 25 degrees Celsius. The other one is 1 mole of H2O gas at 25 degrees Celsius. So for the first pair, we compare 1 mole of H2O solid at negative 25 degrees Celsius with 1 mole of H2O gas at 25 degrees Celsius. So therefore, we can see the substance is the same. So they are both H2O. So therefore, we have the same type of atom, same amount of atom. So for each one H2O, then particularly the question also tell you we have 1 mole of H2O solid, 1 mole of H2O gas. So therefore, the amount in these 2 examples are the same. What are the difference? So the difference are the temperature and the state. So when temperature is negative 25 degrees Celsius, the other temperature is positive 25 degrees Celsius. The state, one is solid, the other one is gas. So we know entropy decreases as the temperature decreases. And when the amount is the same, solid state has a smaller entropy S. So therefore, by compare, we will know 1 mole of H2 gas at a higher 25 degrees Celsius has a greater entropy. So therefore, this 1 mole of this will have a greater entropy. Okay, so the second pair we have 2 mole of NH3 gas. When NH3 is ammonia at 25 degrees Celsius, or 1 mole of NH3 gas at 25 degrees Celsius. So we have 2 mole and 1 mole. So let's compare what are the same, what are the difference. So when we compare 2 mole of NH3 gas at 25 degrees Celsius with 1 mole of NH3 gas at 25 degrees Celsius, and we can see the substance are the same. See, they are both. The substance, both of them are NH3. So same type of atom, same amount of atom, just in this one NH3. So then we can also see the temperature are the same. So both of them 25, 25. 25 here and 25 here. The states are the same. So they both are gas, gas, and gas. So the difference is the amount, how much we have. So in the first example, we have 2 moles. In the second example, we have 1 moles. Okay, so therefore, we know entropy S increases as the amount of matter increases because entropy S is X times C, which means depending on how much we have. The more we have, the more entropy we have. So therefore, the 2 moles of NH3 gas at 25 degrees Celsius has a greater entropy. So therefore, we can say our conclusion will be D. Answer will be D. Okay, so question number 4 is using the standard molar entropy to calculate the standard entropy change delta S for the following reactions. So we have this equation in the 2H2 gas plus O2 gas plus 2H2 liquid. Then we have this table. So in this table, we have H2 gas, O2 gas, H2 liquid. So pay attention to the state of each of those product and reactant. Then we have this S naught or S0, J per Kelvin. So this S naught is the standard molar entropy. So we have different number for different substance. So when you given those S naught and a chemical reaction equation like this, you can use the following formula to calculate delta S naught. So delta S naught equals sigma. Sigma means sum. So the Greek letter sigma means sum. Okay, so sigma means sum. So A is the coefficient for the product, M is the coefficient for the reactant, and S naught is the standard molar entropy. So therefore, just plug those numbers, use this formula. So you start with delta S naught equals sum, depending on how many products we have. For this one, there's only one product, so therefore, we will just take the coefficient for the product. So N for the product equals 2. So we only have one product, so therefore we have 2 what? So we know there will be 2 moles. But you don't have to use this name in this example because so by definition we know there are molar entropies. So therefore, actually, if you write those units completely, so this J per Kelvin should be J per mole per Kelvin. Therefore, if I take this mole here and then I multiply by those numbers, so this S not a product means for whatever the products we have. So we have we'll just write S naught. Our product is only one product, is H2O liquid, and then that later on we'll find out this number and substitute. So then subtract, let's see, really do a sum and use a larger parentheses. So then we identify the coefficient for the reactant. So one reactant is H2 gas, has a coefficient 2, so 2 moles. And then we will multiply this by the molar entropy for that reactant. So that reactant is H2 gas. Then we close that, then adding the other reactant. So the other reactant we have is O2 gas, and the coefficient here is 1. Therefore, we write 1 more, and then we multiply that by the S naught of that reactant, which is O2 gas. Close this bracket and close this other bracket. Okay. So now we can just substitute those numbers. So we can say, as I said, I did not put the unit more in those units. So I think we should have this more in the unit for this S naught. And if I keep write that 2 more, and then I just substitute this number. So let's say for this H2O liquid, so this number become positive 79.91. So 79.91, and the unit is joule per mole per Kelvin. So therefore, this is the product. You can see the more and the more comes out. So then we will do the reactant. So reactant, we can see we have 2 more, and then we times this number. So this is just a name for a number, which means for 130.58. So we have 130.58, and then joule per mole per Kelvin. Okay, don't use bracket yet. So we have we're going to adding the other reactant. All right. So then plus 1 more. So plus 1 more, 1 more come from the coefficient, and then this SO2 gas. SO2 gas as put to the table is 205.0. So it's 205.0 joule per mole per Kelvin. So now you can see the cancellation of those units. So more comes out, more comes out. So everyone should have a joule per Kelvin. All right. So therefore, we will multiply and add and subtract. So we have for the first term, we get 159.82 joule per K, and then we will have these two multiplied and plus this one. So altogether, we get 466.16 J per K. Then do the subtraction, you get negative 306.34 J per Kelvin, and the answer should be D. Okay, so question number 5 is calculate the free energy change for the formation of NO gas from N2 gas and O2 gas at 298 Kelvin. So the equation for the process as described is N2 gas plus O2 gas produces 2 NO gas. So then the given information is delta H naught equals to this much kilojoule. Delta S naught equals 74.7 J per K. So we want you to use these two numbers, calculate that free energy change. So free energy change will be delta G, a standard free energy change will be delta G naught. So then once you get this number for delta G, you want to specify is reactant spontaneous or non-spontaneous. So spontaneous means delta G is negative or less than 0. So there are quite a few different ways to calculate this delta G naught. So when given delta H naught and delta S naught, we can use the following equation to calculate the delta G naught. So delta G naught equals delta H naught minus T times delta S naught. Just need to arrange delta S naught and delta H naught have the same unit and the temperature should be in Kelvin. So because all those given choice is in kilojoule, 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 so therefore we can say this delta H is given in kilojoule, but this delta S is given in joules. So therefore, when we do the calculation, we just need to convert this joule into kilojoules. So the equation you want to use is 1 kilojoules equals 1,000 joules. So therefore, let's begin by using this equation. So delta G naught equals delta H naught. Let's just substitute. So here delta H is 180.7 pJ. So we write that like that. Then next in the formula is this subtracting sign. So just subtracting. Then next will be T, so T should be in Kelvin. So this is okay. So I already give you in Kelvin, so 298 Kelvin. And then you multiply this T by delta S naught. So delta S naught is given as 74.7 Joule per K. So as we said, this first one, or the delta H, has kilojoule, and right now we will have a J because this K and the other K cancel out. So this K cancel out. So therefore, we have to convert from our J to Kj by using this equation. So we'll make a conversion fraction, and we want to cancel out that J. So J is 1000 for 1 kJ. So therefore, we use this conversion and to cancel out that J to get the kJ. So let's see the cancellation to J and J cancel out. So after that, we just multiply and subtract. So we still have this 180.7 kJ. Then we minus this two number multiplied and divided by 1000. So get negative 22.26 kJ. Okay, so this is very important. So don't forget that. If you have two numbers have a different unit, you must convert them in the same unit. So those questions, kind of easy question, but just don't forget to make sure they have the same unit. So you get this much kJ. If we keep tracking the six figure, so we get 158 kJ, which is a positive. So when delta G is positive, the process going forward as described is non-spontaneous. So delta G, or when delta G larger than 0, so the process is non-spontaneous. All right, so therefore the choice will be C. 158 non-spontaneous. Okay, so question number 6. And you want to using the first, you want to using the given data to calculate the standard free energy change for the reaction at 298 Kelvin. And then second part of the question is what is the delta G naught for the reverse of this reaction? So when you have those number like this, so it's called delta G naught F. So that is the so-called standard. So standard comes from this knot. So then when you say G, which means free energy, and then free energy, standard free energy formation. So the formation comes from this letter F. So this is the typical some of those data you can see in the table. And if it give you those number for the substance, it means to produce one more of that substance, what is the free energy change at a standard condition? So we have those this chemical reaction. We have two reactants and one product. We are given the free energy change for the product for the two reactants, and one reactant is given 0 because that is the stable allotrope for chlorine gas. For the phosphorus gas, P4 is also element, but that's not the most stable one. So therefore, that will have a number for the delta G0, not F. So therefore, if we have all the number we need for this chemical reaction, we can use this formula calculation. So very similar as you calculating delta S. So N and M, so this N and M here are the coefficients for the product and for the reactant, and delta G not F is the standard free energy formation. So therefore, now we will just using this formula do the calculations. So then again, this Greek letter means sum or adding. So the first term, first term is for the product. There's only one product, so this is only one product. So the coefficient, so N is 4. Therefore, we write 4. So we know that 4 means 4 moles. And then we write delta G not F for the product. You can specify whatever the product name. So the first product, PCl3 gas, and then subtract sum of those reactants. Probably no, we don't use the sum. No, we just use numbers. Okay, so we have 2 reactants. One reactant is P4 gas, has coefficient 1, so therefore 1 mole. Okay. What that means is this reactant, so N or M equals 1. So this reactant, the M equals 6. So you might have a different, you might have a different M depending on the coefficient for the reactant, or you might have a different N depending on the coefficient for the product. So for the reactant P4 gas, just 1 mole. And then you just write delta G not F and then P4 gas and that. All right. So then inside this larger parentheses, so we have another reactant. Therefore, we're adding other reactant which has the coefficient is 6. So therefore 6 more, then multiply by the delta G not F of that reactant, which is Cl2 gas. So that is for that. Then we close this parentheses. Okay. And then next we are just going to substitute the numbers. So we have we still have the formula from the coefficient. Then this guy, we do the table and see what's the number of that. So that is negative 299.6. Negative 299.6. What are the units? So the unit is kJ per mole. So I'll just write kJ per mole. Then we subtract in the larger parentheses. So we have 1 more, and then the number for this one, with the P4 gas, 24, positive 24.4. So 24.4 kJ per mole. Then we add 6 more, but that one is 0. Okay, so I mean this number is 0. You can see the table here, 0. All right, so therefore we multiply and add. So what we get is let's see, first check the unit conditions. So more and more comes out, more and more comes out. This just becomes 0, don't matter. So negative 1,198.4 kJ and minus 24.4 kJ. That's the last line. And now, okay, so we have equals negative 1,222.8 TGA. Okay, so second part of the question is, if reverse reaction, then the product becomes reactant. So that means you will reverse these two terms. So that becomes the first, and that becomes positive, and that becomes negative. So what happens, that means your delta G will change the sign. So if you have negative delta G for the forward reaction, and your reverse reaction have the positive delta G. So therefore, for the reverse reaction, delta G naught equals positive 1,222.8 TGA. The same number, but the sign opposite. Sign opposite. All right, so therefore, let's see the answer. We have a negative and then positive, so the answer is A. Okay, so question number 7. Question number 7 is in section 5.7, we use Hess's law to calculate the delta H naught for the condensation for the combustion of propane gas at 298 Kelvin. So this equation given, and give you delta H is this number, and so then without using data from appendix C, predicting that delta G for this reaction is more positive or less positive than the delta H. So to do that, we were using this equation. So we can see from this equation, and T is in Kelvin. So if T temperature in Kelvin is always a positive number. So when delta S is positive, so if delta S is positive, then delta G naught equals delta H naught minus, so T times, initially is minus T times delta S. So because T is a positive number, and if delta S is also positive number, so positive number is positive number, so therefore we can just say like qualitatively delta G naught equals delta H naught minus positive number. So the positive number is actually the absolute value of T times delta S naught. So you can think about if you subtracting something by a positive number, so therefore your delta G, whatever the number for delta H, because you are subtracting a positive number, so therefore your delta G becomes less positive than delta H. So oppositely, when delta S naught is negative, then delta G naught equals delta H naught minus a negative number. Why is that? Because this is just the qualitatively reasoning. So in the formula, you can see in this parenthesis is actually you are minus T times delta S. So T is always a positive number, delta S by assumption or in some process is negative. So therefore positive times negative is negative. So therefore, even before you do the calculation with numbers, you know your delta G naught equals delta H naught minus T times delta S. That will become delta G naught equals delta H naught minus a negative number. So minus a negative number you can write as plus a positive number. So then what is the positive number? The positive number will be T times delta S absolute value. So therefore, if we have this, then we know, so delta G will be more positive than delta H because you're adding a positive number. Or you can say delta G is less negative than delta H naught. So for this, now for this given problem, for this given chemical reaction, so we have this given delta H. Now you just have to decide what will be the sign for delta S or for delta S naught. So if you don't use any data to the calculation for delta S naught, you just compare, typically just compare how many gas for the product, how many gas for the reactant. So there is one gas. What I mean by one gas is one gas by the coefficient. Then plus 5 gas or 5 more gas. So altogether we have six gas for the product. Now how many gas? So now how many gas we have for the reactant? So we have the coefficient here 3. So we have 3 gas. And then this is liquid. So therefore plus the other one is 0 gas. So altogether we have 3 gas. So now you compare 3 gas with 6 gas. So obviously the gas state substance decreases from the product to the reactant, or the gas of the product is more. So therefore, there's a larger entropy. So therefore, the larger entropy for the product, which means delta S, is positive, as we expected. So if delta S is positive, so then from the reasoning we can say your delta G will be less positive than delta H. What that means, if you rewrite the equation, so your delta G naught equals delta H naught minus T times delta S naught. So as we reasoned before, so that becomes delta H naught minus what kind of number it is. So that means this in the parentheses. So in the parentheses, T is positive. So we know that from our reasoning, so this is positive. So this is positive. So positive, positive is positive. Therefore, we really minus a positive number. So if you minus a positive number, so for whatever number you minus, so your number will become less positive. Right. So therefore, the answer for this question is A. All right. So the next question is question 8. And for question 8, so we are having this Haber process, and usually the Haber process is written as the opposite. I mean, usually the Haber process is written N2 plus A2 plus N3. But here I just, for the practice, I write it this way. So for this reaction, delta H naught equals 92.38 kJ, delta S naught equals 198.3 J per Kelvin. Assuming delta H naught and delta S naught for this reaction do not change with temperature too much, then I want you to predict the direction in which the delta G for the reaction change with increasing temperature. And the second part is calculate delta G at 25 degrees Celsius and also at 500 degrees Celsius. So similarly as in last question, question number 7, we can see from this equation delta G naught equals delta H naught minus T delta S naught. So when delta S is a positive number, so delta G will be less positive than delta H. So when delta S is a negative number, and delta G naught will be less negative than delta H naught. So that's the conclusion or the reasoning we did in last question, question 7. You can also say is that is kind of we can think about so our this is our Y, and then this is our let's see, this is our intercept, and then we have this two. We can think about our T is our x axis, and then our slope will equals negative delta S naught. So therefore, when you have that let's see the delta S is a positive number in this example. So therefore your slope is a negative number. Slope is negative, that means if you have those y-axis and x-axis, you will have those kind of line. So that means your y will decreases as x increases. And so therefore, in this equation, we see that is true. So we have a delta S, we have delta S for this given prediction is positive. So when this is positive, so then negative positive is negative, therefore we have a negative slope. Therefore we expect it as temperature increases, so delta G will become like a more negative or decreases. Okay, so therefore next we are just going to use those numbers to the really calculations. So what we do, we just change or convert those into the same unit and convert the temperature in kelvins. Okay, you can see in these two given numbers as usual. So delta H is kJ, delta S is J. So therefore, when you do the calculation, you can just see what are the choice. All the choice for the answer is kJ. So we'll keep this kJ for the delta H naught. So 92.38 kJ, and then minus temperature. Let's see, for this temperature, so this is T equals 25 plus 273 equals 298 Kelvin. So therefore, we just see minus 298 Kelvin. And then we substitute our delta S naught, which is 198.3 J per K. So you have to be careful, because if you cancel out, let's say the K with K, you only left with J. So J cannot add on to KJ. So what you do, you have to convert using the equation we write in the question 7. So 1 kJ is 1000 J. Then we can see the J and J cancel out. So we get a kJ plus kJ. I mean the final answer of minus kJ. So that means you can adding or subtracting the same unit. So therefore, let's do the multiply and subtraction or adding, depending on the number. So we keep the first 92.38 kJ. Then we see this 298 times 198.3 divided by 1000 give you 59.09 kJ. So together we get 33.3 kJ. So this is the delta G naught at 25 degrees Celsius. So similarly, we can do the calculation for 500 degrees Celsius. So you can see T at 500 degrees Celsius will be 500 plus 273. That will equals 773 K. So that's for this is the temperature. Now we do the similar calculation for the delta G naught. We're assuming this delta H do not change with temperature, so therefore we'll use the same delta H, even though here will be 500 degrees Celsius or 773 Kelvin, we're still using the same number. So what's changed clearly is this temperature. So now this T becomes 773 Kelvin. And a similar assumption. So we're assuming our delta S naught do not change. Therefore, we use the same 198.3 for our delta S naught as what we did for the 25 degrees Celsius. So the last is you convert the J into kJ by using this conversion fraction. And then you will see, well, it will agree with our prediction. So this Kelvin comes out, this Joule comes out. we get Kj in both this term and this term. So therefore, we can add or subtract. So we write 92.38 kg here. Then these two numbers multiplied and divided by 1,000, we get 153.29 kg. So finally, we get negative 60.9 kg, rounding to the right number of sig figs, we get negative 61 kg. So then we can see we have increased the temperature from 25 to 500, and we can see our delta G decreases as our prediction because the slope is negative. So therefore, we can see it become more negative, and so therefore our choice will be D. Okay, so question number 9 is calculate delta G at 298 Kelvin for a mixture of 2.0 atm into 3.0 atm H2 and 0.50 atm H3 being used in the Haber process. Now I write the Haber process as the opposite way as I write in question number 8. All right, so give you this delta G. So then you want to calculate, this delta G naught, and then want you to calculate the delta G. So delta G, if without the naught, it means at any conditions or non-standard condition. So we're using this equation, and then you can recognize in this equation. So delta G is given. So delta G naught is given. So that equals negative 33.3 pga. So then we know R is the gas law constant, 8.314 joule per mole per Kelvin. And then temperature should be in Kelvin. So giving you T equals 298 Kelvin. And then what is the Q? So Q is the reaction quotient. And we know it has a similar expression or equation as equilibrium constant K. Okay, so therefore, for this equation, and your Q will equals, if we use partial pressure, so we use P, and then P what? We use subscript. So our product is NH3. So therefore, partial pressure of NH3. Then we have the coefficient 2, then we'll square. We'll use that as a square. We have two reactants. One is N2, so N2, coefficient 1. So then we have the H2, coefficient 3. So therefore, that becomes third power. So this is our Q. So now we can just apply everything in the equation. Make sure we will check in the unit for the delta G naught and R. So delta G naught is kilojoule, R is joule. So in your calculation, be very careful with those units. So we substitute, because all those are kilojoules, therefore you will keep this delta G naught 33.3 kilojoule as it is, then plus 8.314 joule per mole per Kelvin, and then times the T. Okay, so I want to erase something. Oh, I thought right here. Let me write here. You don't have to erase that. So that equals delta G equals delta G naught plus RT Ln Q, then negative 33.3 Pj plus 8.314 J over mole per Kelvin. Then our temperature 298 Kelvin. So then we have to multiply by this conversion fraction to convert the joule into pjoules. Then we have this Ln Q. So let's see, our Q will be that. Okay, so let me write them. So we'll write PNH3 2, which means 2 moles. So then, so that PN2 and then PN2 and PH2 3. So 2 here it means 2 more, 3 here means 3 more, 1 means 1 more. So they all have 1 more. So pretty much you can see all those when we multiply and divide. So let me excuse me for this bad bracket. So all together will have the power more. Okay. So if you have more as power by the mass rule, so you can take this more off and put it in front of this Ln. Okay. Therefore, I will rewrite the more here. So between these two guys multiply, then delete this one. So therefore, we will see the unit cancellation very clearly. So don't be confused in your calculation. Don't be confused by this mole. Sometimes you see the textbook write where for delta G kilojoule per mole. Sometimes don't. So when you do a calculation, just make sure this has a kJ, this has a kJ. Don't worry about this mole. So this mole comes out, then this K comes out, and this J comes out. So therefore, we will make it simple, so we don't have to worry about those promos. This textbook sometimes emphasize promo as the reaction is written, but don't really like emphasize where this more comes out in the second term. So what you get is let's say negative 3.3 pj. Then let's say this two number multiply, so you get 2.478, or simply become a kj. So now just times the Ln those numbers or those notations. So you can just go back to the question. You can see what is the partial pressure of NH3 given, which is 0.50, and you square that. Okay? Then what is the partial pressure of N2? So that is given as 2.0 atm. What is the partial pressure of H2 gas, which is 3.0 atm? And with that, you have to raise to the third power. So all of those you want to square, divide, cubic, then take the Ln function. So let's copy this 33.3 kJ here, then plus 2.478 kJ here. Then we get a number from the Ln function. So what you get is negative 5.3752. So that you just finally get negative 46.6 kJ. So the answer is C. Okay, so last question is the standard free energy change for the Haber process at 25 degrees Celsius was obtained in some of those problems. Let's say we have this number. Probably this number will not matching the exact number. We just use this number as a practice. So then you are going to using this value for the delta G to calculate the equilibrium constant for the process at 25 degrees Celsius. So when given delta G naught and you want to calculate the K is the equilibrium constant, then we can use this equation. Okay, so then we can use this equation. So in this equation, you already know, so this R equals 8.314, and which is joule per mole per Kelvin, and T should be in Kelvin, 225 plus 273, but give you 25, and that becomes 298 Kelvin. All right. So then you want to calculate the K. So if you say those numbers like that, so if you keep tracking the unit, you probably don't have to track in this more unit. As I said in the last question, just checking this J with the KJ. And so therefore we will, if you want to see where this more comes out, you can review the question 9. And so here I will just use the number for the delta G naught, and that I get the K. So just substitute. So we have negative 31.3 kJ equals negative 8.314 J per mole per Kelvin, then times 298 Kelvin, okay, then times L and K. Okay. So in the last question, I said in the K, when you write the expression for the K, you will see the coefficient. The coefficient become exponent, and those coefficient has unit mole. Therefore, see, I'm going to say that again. So whenever you see this, that means you will get a mole from this K. Okay, so you will get a mole from this K. So this from that. Right. So therefore, this, if you want to check, you will see check. Otherwise, you don't have to worry about that. So the problem is right now you have J and there's a KJ. So therefore, the one more fraction is convert this J into KJ. So now I kind of ran out of room. So probably I will write this in a different way. Then we can make our conversion here. Okay, so 298 Kelvin. Then we have to write 1 kJ and 1000 J. Then we have that mole from that RNK. All right. So now we can see we can do our K and K come out, then J come out, get as the mole come out. All right. So we will take these numbers. So negative 31.3 kJ. Then here everything together gets negative 2.478 kJ. Now you really have this RNK you want to calculate. So you just divide. So divide this side by negative 2.478 kJ, then divide this by negative 2.478 kJ. So then this cancels out. So here everything comes out. So therefore, what you have here is simply L and K, and then these two numbers divide. So the KJ comes out. Then we get 12.63. All right. So therefore, to find K, we'll take E to the 12.63 equals E to the ln K. So E and ln are anti-function cancel out. So you get K. Then use calculator, so that becomes 3.06 times 10 to the 45. So then the answer is E. All right, so that's it for chapter 10.